Edge detection is a crucial step in image processing, playing a vital role in object recognition, segmentation, and feature extraction. Despite its importance, existing edge detection methods, such as the Canny and Sobel operators, suffer from limitations, including sensitivity to noise and inability to detect weak edges. To address these issues, Hao Shu and Guo-Ping Qiu from Shenzhen University, China, propose a novel approach, dubbed more precise edge detection, or MPED. The MPED algorithm combines gradient operators and non-maximum suppression techniques to detect edges more accurately. A new gradient operator is introduced, which utilizes both horizontal and vertical gradients to detect edges. This operator is designed to be less sensitive to noise and better at detecting weak edges compared to traditional methods. The MPED algorithm involves three key steps. First, the proposed gradient operator is applied to the input image. Second, non-maximum suppression is performed to thin the edges. Finally, a double thresholding technique is applied to determine the final edge map. The authors provide detailed mathematical equations for each step, explaining their purpose and significance. Experimental results demonstrate the superior performance of MPED compared to other state-of-the-art edge detection algorithms on various benchmark datasets. MPED outperforms existing methods in terms of precision, recall, and F1 score, particularly in noisy or low-contrast images. While the proposed method shows promising results, the authors acknowledge its limitations, including computational complexity. Future work includes optimizing the algorithm for real-time applications and extending it to color images. Overall, the paper contributes to the field of image processing by providing a more precise edge detection technique that can improve the accuracy of various computer vision tasks. Edge detection is a fundamental task in computer vision, where the goal is to identify and localize edges in images. Despite its importance, existing datasets and models for edge detection have limitations. The authors of this paper propose a novel data augmentation method that enables more precise predictions on edge maps and ordinary images. This method is demonstrated to outperform previous models on the Brind dataset. The authors also modify data augmentation to allow edge detection models to employ noiseless data for training, resulting in more satisfactory results on noiseless data. This is particularly important, as existing datasets for edge detection tasks, such as BSDS 300, BSDS 500, NYUD, and others, are not specifically designed for edge detection and have noisy annotations that can never be completely accurate. Data augmentations are essential for edge detection tasks, but they come at the cost of increased model training consumption. The authors review various CNN-based edge detection models, including HED, RIND, and DEXI, which output results in multi-scales and multi-levels. They also discuss the importance of loss functions, such as the Berhu loss function used in HED, in edge detection tasks. The author's novel data augmentation method addresses the limitations of existing datasets and models, providing a comprehensive review of previous works in edge detection. By highlighting the problems of noisy annotations and limited datasets, the authors propose novel solutions to improve the accuracy and efficiency of edge detection models. The SDPED model's prediction evaluations and methodology are discussed in this section. The standard procedure for evaluating edge detection models is first explained, including the calculation of optimal dataset scale, optimal image scale, and average precision rate using the F-beta score. The SDPED model's structure is then detailed, which utilizes CSDB and a more complex fusing block compared to previous models. Weight binary cross-entropy loss is used for training. The discussion also covers improving performance on noiseless data by adding noiseless data into training sets and directly labeling data. Finally, the importance of selecting a suitable error toleration distance for evaluations is highlighted. The SDPED model architecture, as depicted in Figure 2, consists of a main path and a button path. The main path includes a feature extractor block, followed by n+2 layers, which comprise multiple cascading skipping dense blocks, CSDBs, and a final block. Each CSDB outputs 21 features, resulting in 21 times n+2 features for the final fusing layer after concatenation. The button path, or fusing block, processes these concatenated features through a 3x3 convolution block, followed by two 1x1 convolution blocks, yielding output feature dimensions of 256, 512, and 1, respectively. A key component of the SDPED model is the cascading skipping dense block, CSDB, illustrated in Figure 3. A typical CSDB block consists of 5 conversion layers, with 64 input features. The first 4 layers each output 32 features, resulting in input feature dimensions of 96, 128, 160, and 192 for the subsequent layers. The final layer outputs 64 features. Multiple SDB blocks are cascaded with skipping connections to form a CSDB, typically comprising 3 SDB blocks. This design enables the model to capture complex patterns and relationships in the data effectively. In the realm of computer vision, edge detection plays a pivotal role. However, evaluating these algorithms has proven to be a challenging task due to inconsistencies in current methods. A key issue lies in the error toleration distance, which significantly impacts evaluation scores. The authors propose that this distance should be set to an exact length of pixels rather than a ratio of the diagonal distance to ensure consistency across different image resolutions. They also suggest a strict error toleration threshold of 1 pixel for evaluations, considering the deviations in human-labeled datasets. The paper presents experiments on various datasets, including BRIND, UDED, MDBD, and BIPED, with specific settings and data augmentations. For instance, training images are split and rotated to obtain 8 augmented images for each image. Labels are added into the training set to improve performance. The authors emphasize the need for a standardized evaluation method that can accurately reflect the performance of edge detection models. They argue that a low error toleration distance is essential to ensure that models are precise and that errors do not make unreasonable contributions to the evaluation scores. Overall, the paper aims to address the limitations of current edge detection evaluation methods and proposes improvements for more accurate and consistent assessments. Researchers have developed a novel edge detection model, SDPED, which leverages a skipping dense structure and multiple layer fusing block to enhance performance. This model is compared to existing models, including HEAD, RCF, RIND, BDCN, and DEXI, across various datasets, such as BRIND, UDED, MDBD, and BIPED. The results demonstrate that SDPED outperforms its predecessors in terms of optimal dataset scale, odds, optimal image scale, OIS, and average precision, AP, scores. Ablation studies on BRIND and UDED datasets verify the effectiveness of the skipping dense structure and the multiple layer fusing block. The improvement of SDPED, particularly in AP scores, can be attributed to the absence of downsample operations, its ability to handle textures, and the design of the CSDB block, which distinguishes edges from textures. The paper emphasizes the significance of preserving information and reducing uncertainty in edge detection tasks. It also highlights the potential benefits of adopting architectures that have proven successful in other computer vision tasks, such as super resolution. By maintaining information and reducing uncertainty, SDPED demonstrates improved performance in edge detection, showcasing the potential of this novel approach. The SDPED model's performance on benchmarks BRIND, UDED, and MDBD is noteworthy, achieving the best results in all 3 experiments with improvements ranging from 2.6% to 8.8% compared to the second-best models. The model's efficiency is highlighted by having the least number of coefficients among all compared models, making it significantly smaller than its predecessors. This efficiency and versatility are demonstrated across multiple datasets, showcasing the model's effectiveness in edge detection tasks. The proposed model's performance on various benchmarks is discussed, with a focus on the improvements achieved. On BRIND and UDED, the model demonstrates its ability to provide more comfortable predictions. In MDBD, the model obtains the best results in all experiments, significantly outperforming the second-best models. Detailed in Tables 3 and IV, the model's performance on different benchmarks and error tolerations showcases its superiority. Notably, the model shows an average improvement of 22.5% over the second-best models in AP, indicating a significant advancement in the field. The ablation study on BRIND and UDED datasets demonstrates the effectiveness of the proposed structures, achieving state-of-the-art results in various benchmarks. A comparison of performance with and without skipping connections reveals the significance of this architectural choice. Furthermore, the impact of using a single fuse layer is highlighted, showcasing its contribution to the model's success. The definition of edges and textures is also explored, emphasizing the importance of noiseless data in achieving accurate results. The paper presents a detailed analysis of the employed models, including SDPED7, which stands out for its compact architecture with the least coefficients yet outperforms other models significantly. The proposed edge detection, ED, models and data augmentation method are shown to be novel and effective, offering a significant improvement over existing approaches. The results validate the structure's validity, underscoring the importance of carefully designed architectures and data pre-processing techniques in edge detection tasks. Edge detection is a fundamental problem in computer vision, playing a crucial role in various tasks such as object recognition, scene understanding, and image segmentation. Despite its importance, edge detection remains a challenging task, particularly in the presence of noise, texture, and varying illumination conditions. Recent advancements in deep learning have led to significant improvements in edge detection, with the development of algorithms such as holistically nested edge detection, deep contour, and bidirectional cascade network. These methods leverage the power of convolutional neural networks to learn rich feature representations, enabling accurate edge detection. The choice of loss function is critical in edge detection, with popular options including the positive sharing loss and the adversarial loss. These loss functions aim to improve edge detection performance by encouraging the model to focus on relevant edges and suppress irrelevant ones. Large-scale datasets, such as the Berkeley segmentation dataset and benchmark, the Pascal VOC dataset, and the Cityscapes dataset, are essential for training and evaluating edge detection models, providing a diverse range of images and annotations. Despite the progress made, current edge detection algorithms still face several limitations. They can be sensitive to image conditions, such as noise and resolution, and may not generalize well to new datasets. Furthermore, existing models can be computationally expensive, limiting their applicability in real-time applications. To address these challenges, future research directions include improving the robustness of edge detectors, developing more efficient models, and exploring the use of multimodal data for edge detection tasks. By highlighting both the achievements and challenges in edge detection research, this review provides a valuable resource for researchers and practitioners working on edge detection and related computer vision problems. The authors of the research paper cite several relevant works in the field of computer vision and image processing. Specifically, they reference Deng et al.'s paper, 39, which focuses on learning to predict crisp boundaries, a crucial aspect of edge detection. This work is relevant to the current research as it explores the importance of boundary prediction in image processing tasks. Additionally, the authors cite Wang et al.'s work, 40, on enhanced super-resolution generative adversarial networks, ESRGAN, a state-of-the-art method for image super-resolution. This reference highlights the connection between edge detection and image super-resolution, as both tasks require accurate boundary prediction. Furthermore, the authors reference a review paper by Mubashar et al., 41, that provides an overview of state-of-the-art datasets and deep neural network-based techniques for edge detection. This review paper is significant as it highlights the current state of edge detection research and underscores the need for continued improvement in this area. These references demonstrate the authors' thorough understanding of the existing literature and their commitment to advancing the field of edge detection.